Today we're working on learning target 3. And learning target 3, we're evaluating limits analytically. And that means using direct substitution, which will be the easiest method, or using other algebraic methods so that we can use direct substitution, which is the easiest method. So in this case, we don't have to look at tables and graphs like we were doing in learning target 2. Okay? So if you have a continuous function, and a continuous function is one that doesn't have any of those holes or gaps or asymptotes like we did in learning target 2, then if we want to evaluate the limit, we can just substitute values into the function and be done. All right? So let's start off with this first idea. It gives you a theorem about some basic limits. Okay? And it gives you some rules, but all these rules mean is that you can substitute your x value into the function to get the y value, which would be the limit. We're going to look at graphs of these as we go. For this first one, for the limit as x approaches 2 of 3. Now 3 is the equation y equals 3. Remember, this is a function. That's always a function. So this is our f of x. If I graph that, y equals 3 is a horizontal line at 3. There are no holes and no gaps, and there's nothing that's going to make it funky. It's just a straight line at y equals 3. Okay? So as x approaches 2, so from the right and from the left, we're approaching this point right here, which is the point 2, 3. There's not a hole there. There's not a gap there. So all we do is we look at the y value. Remember, the limit value is going to be the y value that we think is approaching the y value. So our limit equals 3. There's not a hole there. We just have a point there. Same thing for the next one. Limit as x approaches -4 of x. Well, x again is just your f of x. That means we're graphing the line y equals x. So if we look at a graph, x approaches -4. Well, from this direction and from this direction, we're approaching this point on the graph. That point is at -4, -4. Right? How do I know that? Because I put -4 in for x, y equals -4. So my limit value is just -4. You can do that by directly substituting -4 in for x. Sometimes I think these basic ones are a little bit confusing just because they're so simple. So in the last one, maybe it'll make more sense here. The limit as x approaches 2 for x squared. Well, x squared is a parabola. So as x approaches 2 from both sides, I'm approaching this point on the parabola. All right? So all you need to do, there's no holes or gaps, there's nothing weird happening. All you need to do is take 2 and substitute it into the equation. So you have 2 squared, and that's 4. So limit value is 4. Again, you can directly substitute. You take the x value that you're looking for, and you substitute it into the function. That's all you have to do. If there's no holes or gaps or asymptotes, that is a perfectly sufficient way of finding the limit. Direct substitution is valid for any polynomial function and rational function as long as they have non-zero denominators. So for example, if you have this function x to the third minus 3x squared plus 2, there's no reason to believe it's any division by 0 or anything weird happening here. So if we're looking for the limit as x approaches 2, I could just substitute 2 in for all the x's and it will work out just fine. Same thing for a rational function where you have a function divided by a function. As long as the denominator isn't 0, you can just substitute your x value into the function and get the limit value. It works out just fine. If you have a root, this works. You can just substitute your x value into the root as long as you're not trying to take the square root or an even root of a negative number, because we all know that can't work. Okay? And then composite functions. If you have 2 functions and try to find the limit of f of g of x, then you find the limit of what's on the inside, and then you just find the function value of that limit. That's all you have to do. And we'll practice that. And with the trig values, if you can directly substitute, you should. And it works out because most of those graphs are continuous, right? Tangent and cotangent and secant and cosecant have asymptotes, but if you can get an actual function value, then you're not hitting an asymptote, so you can actually just directly substitute. So all these theorems mean that whenever substitution works, it's a valid method. You should always try to substitute first. Always. It's the easiest. So let's do some examples. First example. I know it's hard to see, but you have a note sheet in front of you with the exact same problem. It says we have f of t equals t times the absolute value of t minus 4. So the first limit is the limit as t approaches 4 of f of t. So if we can substitute 4 in here, and there's nothing wonky going on, then we can get the limit. So that's what we're going to do. So I have 4 times the absolute value of 4 minus 4. Well, the absolute value of 4 minus 4 is absolute value of 0. So I have 4 times 0, and 4 times 0 is 0. So the limit equals 0. We directly substituted. We didn't get a whole or anything. We just got a function value, and that works. So on the second one, the limit as t approaches negative 1 of f of t. Well, then I have negative 1 times negative 1 minus 4. So that's negative 1 times the absolute value of negative 5. You have negative 1 times the absolute value of negative 5, which is 5. And negative 1 times 5 is negative 5. So my function value is negative 5, so my limit must be negative 5. So if you can directly substitute, you should try, right? May as well. We just plug the numbers into the function and they worked out. So if you should always try that first. Don't try some fancy, look at a table, look at a graph, when you can just actually take the numbers and substitute them in. All right, now here's an example of some composite functions. So here I have two different functions. I have f of x equals 4 minus x squared, and then I have g of x equals the square root of x plus 1. So make sure you're looking at the right function that it's asking for when you're doing the limit. So A says find the limit as x approaches 1 of f of x. So that means we're going to use this function highlighted in green because it's f of x. And so I have 4 minus 1 squared plus 4 minus 1, and 4 minus 1 is 3. So that's my limit value. Again, if you can directly substitute, you should. The second one, the limit as x approaches 3 of g of x. So that time we're using the yellow highlighted function, is g of x. And so I have the square root of 3 plus 1, and that's the square root of 4, and the square root of 4 is 2. So my limit is 2. Okay? Now the last one's a composite function. So it says to find the limit as x approaches 1 of g of f of x. So this theorem back here that I skimmed over says again, you can do this by finding the limit of what's on the inside of the parentheses, and then just find the f of whatever that limit is. So we're going to rewrite this as g of the limit as x approaches 1 of f of x. The limit as x approaches 1 of f of x, we already did that. That's what this is. So I know I've got g of 3, right? Well, g of 3 just means we need to put 3 in for x for g of x. So we have the square root of 3 plus 1, which we just did, get the square root of 4, and we get 2 again. So for composite functions, you're just going to rewrite them so you have the limit of what's on the inside of the parentheses. And then just use function notation to substitute into the other function. Okay? For 31, we have secant of 2x. Now, for the trig values, we're going to directly substitute, and then we're going to use the unit circle to get exact values. So if you're using the unit circle, you get exact values. I do not want decimal answers for any of these trig values. Okay? So this is the limit as x approaches 0 for secant of 2x. So if I directly substitute, I get the secant of 2 times 0. That means it's a secant of 0, right? So remember, secant is the reciprocal of cosine, okay? So be careful with that. So I'm going to open my unit circle up so we can look for some things on the unit circle. All right, so looking at the unit circle, we're looking for secant of 0. Well, here's 0 degrees, or 0 radians, so secant of 0. So again, secant is the reciprocal of cosine. So if I find the cosine of 0, the cosine of 0 is 1. Secant of 0 is the reciprocal of that, so 1 over 1. So the secant of 0 equals 1. So for our limit value back here, secant of 0 equals 1. So our limit as x approaches 0 of secant of 2x equals 1. Okay? That should be enough to get you started. So you're going to do the day 1 assignment for Learning Target 3. You need to try substituting the values in order to get your limit value.